We saw from an example that when you have sinusoidal forcing in a second order system and the angular frequency of the forcing is equal to the natural angular frequency of the system, we get this resonance behavior where the amplitude of the response goes to infinity as time goes to infinity. So that's a really interesting phenomenon, and really it's what makes these systems sort of important. So it's worth looking into it more. Also, in the in those examples, we had no damping, and it would be a good idea to know how damping affects the whole resonance situation. So what we're going to do is find a particular solution for this differential equation, y double prime plus 2 lambda y prime plus omega squared y equals sine of gamma t. So remember, if you have a mass spring type setup or an electric circuit, an RCL circuit, then you can write lambda and omega in terms of the constants of that system. So, for example, lambda is it's in the mass spring situation, it's beta over 2 times mass, and omega is the square root of k over m. And you can also write them in terms of your circuit components if you want to. So we're going to work with lambda and omega just to sort of have fewer symbols to juggle around, but you can always translate back to your mass spring constants or your circuit components if you want to. Also, the amplitude of the forcing that we have right here is 1. If you want to change the amplitude, you can just multiply this by whatever amplitude you want. Let's call it f sub 0. And what you'll see is that the particular solution just also gets multiplied by the same constant. So just to have fewer symbols floating around, I'm not going to have an arbitrary amplitude. We'll just have the amplitude 1. Okay, so let's dive in. To find a particular solution, of course, we have to know what the complementary solution is so that we don't accidentally overlap with it. So the characteristic equation for the associated homogeneous equation is r squared plus 2 lambda r plus omega squared. So the roots are equal 0. So the roots are minus 2 lambda plus or minus the square root of 4 lambda squared minus 4 omega squared all over 2. And then if you simplify this, you get minus lambda plus or minus the square root of lambda squared minus omega squared. Okay, and depending on whether you're overdamped, underdamped, or critically damped, right? The stuff inside of this square root might be positive, negative, or 0. If it's positive, so if lambda squared minus omega squared is positive, then you're underdamped and you have 2 real roots, in which case your solutions for your fundamental set of solutions for the associated homogeneous equation are going to look like e to some power times t. If lambda squared minus omega squared is equal to 0, then your 2 solutions are going to look like e times some negative coefficient times t and t times e times whatever that negative coefficient is times t. I say whatever that negative coefficient is. We can actually write down what it is. It's lambda. And then in the underdamped case, this is where lambda squared minus omega squared is less than 0. In that case, your values for r, this is sort of in many applications, this is the most important case. And in this case, your roots to your characteristic equation are minus lambda plus or minus square root of omega squared minus lambda squared times I, and then your fundamental set of solutions are going to be e to the minus lambda sine of, I don't have room for it, but it's sine of square root omega squared minus lambda squared, and e to the minus lambda times cosine of square root omega squared minus lambda squared times t. Okay, so, in applications, right, we looked at least one example where the forcing was exactly equal to this frequency of the characteristic equation. But in actual applications, it's impossible to exactly match this frequency, right? In the physical world, it's impossible to make two frequencies exactly the same. In applications, we don't really have to worry about accidentally having our forcing overlap with this complementary solution, because it's just impossible to make the frequencies match down to the infinite decimal place. So for our particular solution here, we can just guess some constant times sine gamma t plus some other constant times cosine gamma t, right? Which is what we wanted to guess in the first place. So now we can start taking some derivatives to do undetermined coefficients. So we get gamma a cosine gamma t minus gamma b sine gamma t. The second derivative is minus gamma squared a sine gamma t minus gamma squared b cosine gamma t. Okay, now we can plug everything into the differential equation. And as usual, I'm going to factor out the sine and cosine gamma t right from the very start. So for sine gamma t, let's see, we have a term with sine gamma t here, here, and here. So the term from y double prime is minus gamma squared a. The term from y prime is minus gamma b, but remember it's also multiplied by 2 lambda. So minus 2 lambda gamma b. And then from y sub p, there's an a, but remember also we have to multiply by omega squared over here, so plus omega squared a. Okay, then there are our terms with cosine. And there are 3 terms with cosines, here, here, and here. So from the second derivative, we get a minus gamma squared b. From the first derivative, we get a plus 2 lambda gamma a. And then from the from the 0th derivative, we get a plus omega squared b. And this all is supposed to be equal to the forcing on the right-hand side, which is sine gamma t. Okay, so now let's take this, let's move this down here, and remember we have to compare coefficients. So the coefficient in front of sine on the left has to be equal to the coefficient in front of sine on the right, and the coefficient in front of cosine on the left has to be equal to the coefficient on cosine on the right, which is 0. So we get, while we're doing that, let's also gather up the a's and the b's. So we'll gather up our 2 terms with a's. So for the red terms, the coefficients on sine, we get omega squared minus gamma squared times A plus minus 2 lambda gamma B, and that has to be equal to the coefficient on sine on the right-hand side, which is 1. And then for coefficients on cosines, for A's we have 2 lambda gamma A plus, and then we'll factor out the B from the remaining terms. We have omega squared minus gamma squared, and this all has to be equal to 0. Okay, now we have to solve this system of two equations for capital A and capital B. This is, unfortunately quite a mess, but that's the life we live, so we have to deal with it. Let's solve for B first, I guess. We'll take the second equation and solve for B. So we get B is minus 2 lambda gamma over omega squared minus gamma squared times A. Now we can put that into the first equation. We get omega squared minus gamma squared times A, which, I'm sorry, I'm putting this in the wrong place. So omega squared minus gamma squared times A. And now we have to plug in this mess for B. So plus 4 lambda squared gamma squared over omega squared minus gamma squared A equals 1. Okay. Yes. Now, factor out the A, right? We've got to add these things. So we get omega squared minus gamma squared squared plus 4 lambda squared gamma squared over omega squared minus gamma squared times A equals 1. So, finally, we get A is omega squared minus gamma squared over this whole mess. Omega squared minus gamma squared squared plus 4 lambda squared gamma squared. Okay, B, right, we take our value for A and plug it back in up here. And fortunately, some things cancel, so it's actually not that bad. You get minus 2 lambda gamma over omega squared minus gamma squared plus 4 lambda squared gamma squared. Okay, so our particular solution is, I'm not going to write it out, but it's this big mess for A times sine gamma t plus this big mess for B times cosine gamma t. Okay, now one of the main questions that we had about resonance was what is the amplitude of this steady state? So remember, this is the steady state solution. And the most interesting thing about resonance is that for some choices of gamma, the amplitude of your steady state is much, much larger than the amplitude of the forcing. So let's actually figure out the amplitude of this. So amplitude of y sub p, remember it's the square root of a squared plus b squared, which is going to be, a real mess. So it's the square root of omega squared minus gamma squared squared plus 4 lambda squared gamma squared over omega squared minus gamma squared squared plus 4 lambda squared gamma squared squared. Okay, and then when we simplify this, it actually isn't as bad as it first appeared. So, a lot of this simplifies and you get 1 over the square root of omega squared minus gamma squared squared plus 4 lambda squared gamma squared. Okay, so we did it. That's the amplitude of the response. Now, this formula is honestly not that enlightening, but what it lets us do is experiment with different values of gamma. So remember, gamma is the amplitude, the angular frequency of the forcing. And remember, omega is the natural frequency, angular frequency of the mass and spring, or the inductor capacitor. And then omega squared, square root of omega squared minus gamma squared is the angular frequency of the mass and spring system with the damping. So mass, spring, damping. So what we're imagining is that we have a mass and spring setup, and we're providing some external force at a certain frequency. And our question is, if we vary the frequency of this external force, what happens? So what we should do is treat this gamma like a variable and plot this function as a function of gamma. So what to do with omega and lambda? Well, we're just going to choose some numbers for omega and lambda. So here I have somewhere, there it is. Here I have a graph of what that function looks like. Right now I have omega set as 1 and lambda set as 0. And on the horizontal axis, this is gamma, the angular speed of the forcing function. Now you can see, just like in the example that we looked at, with zero damping, right? So lambda is our damping, playing the role of our damping coefficient. With 0 damping, when the forcing angular speed, gamma, is equal to the natural angular speed, omega, we get an infinitely tall response. Now, the particular solution isn't always at this amplitude, but it does reach this amplitude. So when your forcing frequency is equal to the natural frequency, that's when you get resonance. So you get this infinitely tall amplitude response. Now our question was, I guess before we add damping into this, if you change the natural frequency of the system just by changing omega, it changes the frequency where you get resonance, which makes perfect sense, right? Because resonance happens when the angular speed of the forcing, gamma, is equal to the natural angular speed of the system, omega. So that frequency at which you get resonance is omega. So if omega changes, resonance changes to follow. Okay, now before we add damping, there's one other thing to point out, which is what happens for the extremes of gamma. So if gamma is very small, that means your forcing is very, very slow. And if your forcing is slow, then the amplitude of the response is 1. But that was the amplitude of the forcing. So what this means is, if your forcing is very slow, the system has plenty of time to react to the forcing, and so the system just follows the forcing around. So that makes perfect sense. Now what happens when your forcing is very fast? So this is when gamma is very large. When gamma is very large, the amplitude of the response is very small. that also makes sense because if you're, right, the natural frequency omega is sort of the speed at which the system can respond well. If you're forcing the system much, much faster than it can respond, what does it do? Well, it doesn't do anything. It doesn't have any time to respond. So if the angular speed of your forcing is very much larger than omega, the system doesn't respond at all, and your particular solution, or your steady state, has very small and almost zero amplitude. Okay, so with all that said, finally let's add some damping to the system. So all I'm going to do is increase this damping coefficient a little bit. So we're essentially adding friction to the system, or adding resistance if we're talking about an electrical circuit. So when we add a little bit of resistance, that maximum amplitude, it doesn't go up to infinity anymore, but it's still much, much larger, right? The amplitude of the response here is much, much larger than the amplitude of the forcing. Remember, the forcing had constant amplitude 1 in this situation. If you make your damping large enough, then there's essentially no resonance, right? There's just so much friction in the system that the system can't really respond to the forcing at all. But as long as your damping coefficient, as long as your friction or resistance isn't too large, then you get a much larger response from the system than the forcing is putting in. And that's why resonance is such an important phenomenon. It lets very small inputs produce very large outputs, as long as the input is close to the natural frequency of the system.